Hello, I'm Vlad, and I'm glad to present my teaching experience in computational electrochemistry. In particular, in that example, I'm going to talk about 20 years of progress in oxygen reduction research on a laptop. It's because during seminar of about 2 hours, we are using laptops, in particular this Google Notebooks, and we learn how to make predictions and then connect them to experimental data. If we're talking about oxygen electrolysis, I have modules which are listed here. And as an example, I will take the effects in electrolysis because these are most vivid and also most clear in regard how to connect the predictions to experiments. For example, we'll take this experimental plot that tells us that we need to weaken the OH absorption on platinum by around 0.1 eV, and that will give us a better catalyst. So we use this guideline in order to study other effects, which are, for example, electronic, facet coordination, ligand, strain, curvature, and anion. I could put more, but of course, I'm limited by 2 hours, so with the students, we can take a look only on these six. For instance, electronic effect is very well known. It can be related to the electronic structure, to the Sabatier principle. What we essentially do, we choose some metals and we calculate their electronic properties and OH absorption energy. Then we plot it. And we discussed that this silver, palladium, and platinum and iridium usually used to make a composition of high entropy alloys. That's exactly for the reason to weaken the OH absorption on platinum by some meaningful value to get weaker absorption, better catalyst. Now, with the same aim, we can go and study the strain effects, where instead of a model like this with lantanoid atoms, we can create a simpler model, and then we change the lattice parameter here. Again, as a result, we get a plot, and we start discussing that it doesn't look linear at all, but it has two semi-linear regions, and we are probably interested in this one because this is when we strain the platinum skin, we destabilize OH absorption. Then we can go to ligand effect, where we have copper atoms in the second layer. We can create some simple models. Of course, in the real study, we will create more models and account for different combinations of atoms. But here it's enough to have 2 by 2 and then change the number of copper atoms in the second layer to get a nonlinear graph like this. And from this graph, by interpolating, we would say that we need a composition of about 0.6 in order to achieve the destabilization of 0.1 eV. And that's approximately what we can see in the experiment. When we change the composition of the second layer, we achieve the optimum, which is around 0.6 or 60% of copper. Maybe more, maybe less. That's how we use the guidance in order to get a better catalyst, and then iteratively we can make both the experiment and the simulations better and better. Let me talk also about, for example, coordination effects. That's when we have different nanoparticles or facets of platinum, and then depending on the number of neighbors, we can assign coordination number and make some correlation. That would be a bit more sophisticated Python scripts, but remember that would be maybe the 10th seminar we are having, so by that time any student can learn some basic of Python and at least can understand what's going on here. Then we define some function. Just to be on the same line, we always can take a look on the model from top from side, or even more sophisticated models like here, where you have some lonely atoms of platinum with coordination of about 5. We plot all the calculated absorption energies. The correlation doesn't look very well, but what we learned is that when you have an edge of platinum atoms, on that edge, the OH absorption will be stronger than on platinum 111. Is it good or bad? That we can discuss with the students. Is it good correlation? That we can discuss with the students. How do we do research? Both experimentators and theoreticians together. That is a topic of discussion once we get this plot and then open some articles. And finally, yes, this is a dual atom site catalyst. That is one of my studies. We curved the material in the model and we can get a nonlinear graph like this. Whatever curvature we put in, we will have a value on this line. And finally, if we're talking about molecular catalyst, this is iron phthalate cyanide, pretty famous. It has two sides. On one, we can run the oxygen reduction. On the other one, we can put an ion, and that's what we can study, the effect of ions. We again get a plot, looks like this. We can start discussing whether it's good to destabilize OH absorption on iron phthalocyanine, or is it not what we desire? How much do we need to destabilize, etc., etc. So with this approach, I'm teaching how to. So I suggest that I can give the same tutorials to your students during some summer schools or online. Thank you for your attention.